Swayam Prabha. Digital India. Educated India.
So, we had been discussing thermodynamics and we talked about various quantities like quantities like temperature, pressure, volume, internal energy, the work, heat. So various types of quantities are there in thermodynamics and we deal with it. We know how to deal with them, deal with these quantities if we know thermodynamics. Now, these quantities may be small, so small incremental change or small changes of these quantities we denote by say the small changes. Small changes are like I call it say delta T, delta P. Similarly, it is delta V, delta E, delta W, delta Q. So automatically you will be tempted to write these things for small quantities. That there is no harm about it when I mean that they are really small. But how small they are. So we need some qualification about that particular statement of smallness in thermodynamics. So can we write? So the question is the following: can we write small quantity as a differential of a function? Say the question is now. So question is now: can we write a small quantity as a differential of a function? As a differential of a function. So that means that we need to have some added qualification on my statement of these delta T, delta V, delta E, delta Q, delta W, and so on. So the how to handle such a question? So that needs a mathematical clear-cut answer. So next question is, what is meant by a differential of a function? So differential of a function means that is the difference between the functions calculated at two neighboring points. So differential by definition what means that a differential is the simple difference the function at the two neighboring points. Let us see that now let us take an example. Example is the following. Say, let us say that f is a function of x. F is a function of x. Then differential by this is a function of a single variable, a function of a single variable. Then the differential means what? I have two different points, the neighboring points. Say a differential means I calculate df as f of x plus dx minus of f of x. It is as simple as this. So you have two neighboring points, one is x and another is x plus dx. You calculate the function at fx and fx plus dx. So if you take the difference, that is called the differential. That is the definition, that is called the differential. Now, can I write any of these quantity as a differential of this function of a single variable? That is the question. So to do this, we need something more. So what is meant by a derivative? So to calculate this quantity, what is this quantity? To calculate this quantity, let us to know what is this quantity, because for the single variable case is almost trivial, but let me put it in right form. That so fx, we know that d of fx dx, this is a differential. By definition, this is f of x plus delta x minus f of delta x divided by delta x, and we take the limit when delta x tends to 0. So that is the definition of what is called of a derivative. This is the first step to calculus that we all know. So I am repeating that statement. I am trying to recollect that in the context of this, because I have a definite intention of answering this particular question. So this means that if you write this fx, but from this it may follow immediately. This is basically the derivative. So it is d of f and d of x. Okay, so ddx of fx. But this is, I have written this delta x, delta x, this is delta x in the same two small changes, but I allow the small changes to tend to go to 0. So this is a limit, is a definite operation. So that means, and if you take this f of x, then I can write as d of fx dx times delta x kind of thing, and in the appropriate limit, or you can write it more correctly in the, when you have taken the limit, it means it is basically dx. After the limiting operation, so it should be the basic thing. So if I put it and fx, so fx minus this, so it should be fx plus of f of x. So fx minus this is basically this into this. Okay, in the limit when x going to 0. This is for a single variable, is as simple as it. So if we write it, this quantity, then what is this quantity? Fx and fx, they get cancelled out, and I have a simple definition. There is nothing great about it, but for a one variable, that is df dx times dx. So df is a differential that I call that the difference is basically a differential. If this derivative exists, means if this limit exists. Okay, if existence of this limit assures that this definition, this differential will exist. It is almost a trivial case for a single variable. Now we come to the two variable case. This is for a single. Now f is now, let for f of xy function of two variables, a function to, if f of xy is a function of two variables, then I can extend the definition. So I can extend this definition. This is, let's say, definition say 1. So I extend extend 1 to include this case. That means if I write f of x plus dx, then y plus dy that is equal to, I can write it. Now what I will do, since I have two variables, I will use partial derivative. That means del as if they are single variable, del f del x when y is a constant, I keep that y, and this is dx plus, take the another case, del of fx del y when x is a constant, and that is dy plus f of x. It means it is a simple extension of this functional relation expansion in two variables. So if I do it, then for now df for two variable, what is when f is a function of fx, x and y, that is what equal to f of x plus dx y plus dy minus f of xy, and that is equal to, now if you write this here, so what you get, these two cancel out, okay. So you have only this quantity and you have del f del x y dx plus del f del y x dy. So this is the definition of a differential of a function of two variable. Why I am interested in function of two variable? Because many of the equation of state, when you are trying to define it, then one of the variables can be defined in terms of the other variables. Okay. So if x and y are independent variables, f is a dependent variable, then df is a differential of that function, and I can take it as a small quantity. Coming back to this question, if these two derivatives exist, and if I write it as f of dx and plus g of dx, so I can write it in this way. Just in this case, it was a function of only fx times x, so it was trivial. It was f of dx. Here it is f of dx plus g of dy. Sorry. So g f of g gy. So the differential of this function is basically composed of two incremental changes here, f and g. But is that all? Now you can see that from this relation, f, it turns out that what is f? I have defined f is basically del f del x when y is kept constant, and g is equal to del f del y when x is kept constant. And from this you can write immediately that del f, when you differentiate with respect to y, because f, y is kept constant here, now I try to vary it, then del f del y equal to del square f, that is del y del x. Now here you have x is constant, so if I write del g del x, that is equal to del square f del x del y. Now you see the order of differentiation is not that important here because they are smooth functions. So from these two, it follows that del f del y equal to del g del x. This condition has to be satisfied by for the function. So if this condition exists, then I call the df is a differential of, so the first condition is they must exist, of course. So existence of all derivatives are there, we assume that they exist, but in addition, so df function f, this is a perfect is a differential if this del f del y equal to del G del X condition holds good. Now this is the perfect differential in terms of mathematics. So we call it exact differential. So when I write this df, so delta f, all delta f's are not df. All these delta f's are not df, but some of them are delta actually df and some are not. Because if they are functions of the two variable, then these conditions must hold good, because f and g both are the functions of x and y. So fx is a function of x and y, and f as defined in terms of this derivative, they actually satisfy this relation and to make this as a perfect differential. So we call it a differential or exact differential. Now let us see which of the quantities can be. Let us take some example. Say f of x y equal to say x square y dx plus say y x y square then dy. So question is it a perfect differential? So you can see that now this is basically this f of x, and this is basically the differential of f is basically df, and so that in terms of this x square y x y square. So I put it this particular relation to check whether df is a perfect differential. Now the question, this is now f, and say this is small g, this is now f, and this is basically g according to this scheme. So the question, if you calculate that what is my del f del y has to be equal to this one. So del f del y is basically x square. See from this one, it is just x square, and here del f del x equal to y square. So they are not equal. So this df is not an exact differential. Del g del x. So this is basically, this quantity is, these two are not equal. So therefore df not an exact differential. We take another quantity, say df of xy equal to, I write say xy square dx plus yx square dy. Then this is basically, this is f. So if I want to differentiate it, then it gives then del f del y del f del y, that is basically 2xy, and del f del f del x, sorry, del g del x, that is equal to again 2xy, 2x. So you see del f del y is 2xy and del g del x, so this is g, so del g del x is 2xy. So they are equal. So this is this df d of f of x, this df when written in this way, and exact differential. What does it mean? So this is for pure functions that we are considering without putting any restrictions that they are thermodynamic functions or something like that. It is just a question of just a question that whether you can treat a small quantity as a differential of a function. That is the only thing. Now come to another concrete example. So another example that you may consider here, this is simple, and if I take it, that comes purely from thermodynamics. Now you take, say, y, say I take another example, take now say w. So if I take dw, if I write it dw, I write it as p times dv. Is it an exact differential? So you can see, you must identify that this is a function of two variables. There are two variables, say it is p and v. So I can write it as, p dv plus v times dp, and of course this is 0. I can write it in this way. I can write p dv as p dv plus 0 times dp. It means that I have expressed this side as a function, I have expressed w as a function of two variables, p and v. This difficulty arises for the two variable case because of this, because of the fact that they are actually involving two variables. But one of the function here, say g, the other case is here simply 0, because dp you can always write. So if this is so, then it is basically f, and this is basically the g in our in our language or in this scheme. So this means that I have basically del f, so del f del p, del f del p equal to 1, and here del g del v, that is basically equal to 0. So one cannot be equal to 0. So dw is not an exact differential. So dw not an exact differential. So now to distinguish between the real differential, or what is called exact differential, and which are not really the differential, but they are only can be treated as small quantities, then I needed change some notation should be put for it. So for exact differential, what I can write for exact differential this quantity. For exact differential, and exact differential I may write, say, d of, say, f. Sorry, d of f means it is a differential of a function of f. Function of, say, two variable. F may be a function of two variable, one variable. Now, for an inexact, that means which is not a differential, example is this for an inexact differential, we call it df. If your df, if the small quantity is not an exact differential, it should be put a cross over this horizontal cross over it to distinguish it from the pure differential. An example here is, say, dE is an exact differential. dF example is dW. So similarly, dQ, dW, they are inexact. Inexact differential, because they depend on the path or depend on the process by which we carry over the change of state. So that's why dq and dw are inexact differential, whereas dE is some change. Now, in this particular spirit, if I look back what to the main formulation of thermodynamics, or the first law, that means we wrote down the first law for finite process. So for a finite process, first law of thermodynamics was stated as delta E equal to dQ minus W. That means Q amount of heat enters into the system and the system does W amount of work. So Q minus W can be equated to dE. So delta E. That is basically, so I can write it as in a differential form. So for small changes, I can write dE equal to dQ minus dW. Note that for small, this is a differential, but they are not real differentials. They are small quantities only. So this is a differential, an exact differential, and they are not. Now, I can restate the first law in a slightly different way, that if I do work on a system in a cyclic way, then the heat gained by the system, if it is equal, heat gained by the system is equal to the total output of work done by the system. So if I state in this way, so for a cyclic process, I cannot think of this dE, because over a cyclic process, system has come back to its initial state. So once it is in the initial state, there is no differential of dE, anything. So the entire thing is zero. So I have a condition for a cyclic process. If a system takes dQ amount of heat from the surrounding and does dW amount of work, work, then I can write for a cyclic process, then dq is equal to dw. Now this is a notation. This cycle, this round actually means that this is a cyclic process, and as if we are doing a summation over the small steps, over the small changes when we attach the system to a particular bath, and the system does some amount of work W for each step, dW for each step. I sum over all of it, and they are equal. So this is also a statement of the first law of thermodynamics, and we immediately see that d of dq minus d of w, that is equal to 0. And now since this is something that is because of the first law, this is equal to dE. Now we see that this is a perfect differential and this is equal to 0. And this means that if the differential of a function over a cyclic process is 0, then E must be a function of that state. So basically E is a function of the state of the system. And this is also a statement of the first law of thermodynamics, and it is a property. And E is a property of the system. And this has nothing to do with any change of state, nothing to do with the process by which we make a change of state. So E is the internal energy, is a state function. Next step, in the next lecture, I will try to develop what this property is and how as a two variable, if it is a function of two variables like temperature and volume, how does it behave? So with that, we close this one and move on to the next